Okay, today we're going to be looking at partial fractions. So previously, you'll have come across questions like this of the form 5x plus 3 plus 4 over x minus 2. And you would have been adding these functions together and you would have got something like this. 5x minus 2 plus 4x plus 3 all over x plus 3 x minus 2 and then sorting out the bit at the top, it would come out as 9x plus 12 over x plus 3 x minus 2. And this is an example where the denominator it's this denominator here has two distinct linear functions. So this one and this one. Now what we're going to be doing today is learning how to decompose things that look like this back into fractions, and this is called partial functions. So there's going to be three kind of categories of partial functions, and the first one that we're going to do is where we have these two linear functions in the denominator. So if we have a partial algebraic fraction of the form px plus q all over ax plus b times cx plus d, that is equivalent of something a over ax plus b plus b over cx plus d. And that's what we've got here. We have, if you look at this, is like this fraction here where you've got the two linear functions like we have down the bottom, and then we have a function on the top, and then when we split it up back into partial fractions, you have a and b, and you have your linear functions as the denominators here and here. We can take this a step further. Say we had ax plus b, cx plus d, ex plus f. It would be the equivalent of ax plus b cx plus b plus big C ex plus f. So let's have a look at how to actually go about this. So we're going to do an example to explore this further. So let's say we've got, so if you have a question in the form express 2x minus 13 over 2x plus 1, oops, I'll not put the 1 in, x minus 3, and we want to express it in partial functions. So we have in our denominator two linear functions. So we know it's going to be of the form, I keep missing out this one, there we go, plus b 3x minus 3. And what we're going to do is we're going to take our denominator over here and we're going to multiply through by 2x plus 1 x minus 3, and that'll get rid of this, so we'll end up with 2x minus 13. So we'll get rid of our denominators, is going to be equal to a. Now this is 2x plus 1, so it's going to cancel with that, so we'll get 3, x minus 3 plus the 3x, x minus 3 will cancel here, so we'll have b 2x plus 1. Now we're going to call this equation 1. And there's two methods to go about this. So this is our first method, where we are going to just look at this and we're going to think about what's a good value to let x be. Let's let x be something. So that we're going to have one unknown, because we can solve for one unknown. So if we were to have x equal to 3, this bit here is going to become 0, so we'll get rid of this whole term. So let's do this. So 2 times 3 is 6 minus 13 is going to be equal to b. 2 times 3 is 6 plus 1, and that becomes minus 7 equals 7b. So b must be equal to minus 1. Now, let's look at this again. What about this? How can we get this to be minus 1? To be 0. So 2x plus 1 equal to 0. X would be minus a half. So let's x be minus a half. So we're going to have 2 minus a half minus 13 equals a minus a half minus 3 is equal plus b 2 minus a half plus 1. So we'll then get, working all this out, you'll get minus 14 equals minus 7 over 2a. So a is going to be 4. So our partial functions will be, the solution will be, let's just rewrite this. A is 4. Plus, it's minus. Be minus 1 over x minus 3. Now we can do an equating of coefficients by setting up a couple of simultaneous equations. So our second method is, so we already had 2x minus 13 is equivalent to a x minus 3 plus b x plus 2x plus 1. And that's just what we had when we first began the question. Now what we can do here is we can multiply the brackets out. So we can equate coefficients. So here we're going to have a plus 2b x minus 3a plus b. And that is, and we've got 2x minus 13. So if you equate coefficients, the x coefficient is going to be a plus 2b must be equal to 2. And 13 must be equal to this. So we have minus 3a plus b must be equal to minus 13. So here's equation 1, here's equation 2, and now we have some simultaneous equations to solve. So by doing this, we can solve the simultaneous equations. I won't work through the solving of the simultaneous equations because it's pretty simple. We've done it all before. A would be 4, b would be minus 1. If you need to go over simultaneous equations, do so. And that gives us what we had previously. Now let's look at another case. So we also have, when we were doing, we can also have fractions of this form. And then if we add these together, we'll end up with 3x plus 1 plus 2. I'm not going to do all the steps. 1 squared, just tidy that up, becomes x plus 1 squared. So, in this case, the denominator sorry, is one linear equation. Well, one linear function repeated, i.e. squared. So the same function is you've got x plus 1 times x plus 1. So you've got the squared. So you've got this one linear function here. Now, when we have this situation, we would split up our into partial functions, fractions even, would become a over, now let's think about this. Here we had ax plus b, and there's a squared one, ax plus b squared. So this would be our general rule when the denominator is a repeated linear factor, this function squared. So let's look at this as an example. So we've got 2x minus 11 over x minus 4, squared. And we want to write this as a partial fraction. So we have our a over x minus 4 plus our b, plus x minus 4 squared. And this time we're going to do the same process. We're going to take this denominator and multiply through by it. So we'll have 2x minus 11 is equal to a. So we'll end up with 1 here, x minus 4 plus b. And this is going to be our equation 1. So again, let's look to get rid of this part. So let's choose a value for x. We're going to let x be 4, so that'll become 0. So 2 times 4 is 8, minus 11 equals b, so b equals minus 3. And now we are going to choose just any value of x that will be simple to deal with. So we're going to let x equal 0, so we'll get on minus 11 equals a minus 4, and we know b is minus 3, so now we can solve for this and get a is equal to 2. So here we get 2x minus 11 over x minus 4 squared equals 2, the value of a, x minus 4, minus 3, x minus 4 squared. Now let's do one that's a bit more tricky. So we've got 1 minus 9 x minus 8 x squared all over x minus 2, 2x plus 3 squared. Now this one here is a combination of the two that we've just had. So we'll be able to write a as a over x minus 2, and then we could write, have some, I'm going to call it some other function here, ax plus b over 2x plus 3 squared. We would end up, if we split this into two other fractions, but we're not going to do it this way because we're just giving ourselves extra work. So we're just going to, that whole process of splitting the function with that's squared is, we're just going to keep going with that. So this is b, and then we'd have our 2x plus 3, I hope that made sense, plus c over 2x plus 3 squared. So you see how we started off with this linear function here, which is this bit here, and then we've deconstructed this part into this form like we did in our previous example. So this time we're going to multiply through by this. We're going to multiply through and we will get 1 minus 9x minus 8x squared equals a 2x plus 3 squared plus b 2x x minus 2 2x plus 3 plus c x minus 2. Now let's look at this first, see if there's anything we can do to make this simpler. Now say if we have x, let's let x equal 2, and then we'll get rid of both of these parts of the equation. So we will have 1 minus 9 times 2 minus 8, 2 squared is 4, equals a 2 times 2 is 4 plus 3 squared. That'll give us minus 49 equals 49a, so a equals 1. Now let's get this bit to be 0. So if we have 2x plus 3 equals 0, x must be minus 3 over 2. So let's let x equal minus 3 over 2. So if we do that, we get 1 minus 9 minus 3 over 2 minus 8 times minus 3 over 2 squared equals, this is going to be 0. This bit will be 0, so we'll just have c minus 3 over 2 minus 2. Working all that out, we will find that minus 7 over 2 equals minus 7 over 2c, so c equals 1. Now let's let x equal 0 so we can get rid of all this. So let's let x equal 0, because that's going to give us the simplest thing to work with, and we can substitute in for a and c. So we're going to have 1 equals 3 squared a, b is what we're trying to work out, plus minus 2 b minus 2 3 plus c's 1, so it's just going to be, oh, not plus, minus 2. That's 1, that's 0, so minus 2. And working all that out, we will get, I should put b a in as well. What was a? A was 1. So it's just going to be 3 squared. So b, working all that out, becomes minus 2. So our partial fractions for this are a was 1, b was minus 2, so that should be a minus, not a plus. C was 1. Let's look at our third class of functions. So previously you would have seen something like 2x minus 1 plus 3x squared plus 5, and once you do all the maths and sort this out, you'd get a function like this. 2x squared plus 3x plus 7 is x minus 1 x squared plus 5. So here you have your linear function and your quadratic. So the rule for this is px plus q over ax plus b. What does it look like in x? There we go. Plus cx squared plus d. Oh no, it's not a plus, sorry. That's multiplied by, sorry, that doesn't help. Is of the form ax plus b plus bx plus c. So you will have a function, a linear function on the top. Cx squared plus d. So there's our quadratic. Now let's do an example. And it's again, we're just going through this. The methodology is pretty much the same for each one of these. Once you remember the general rule for setting up your partial equation. X minus 1, x squared plus 2. So we'll have our a over our linear plus, now we've got our linear equation up here, bx plus c over our quadratic equation, x squared plus 2. Now this time we're going to multiply by this denominator. So again, we're just going through the same steps each time. 8 2x minus x squared equals, now this is going to be a x squared plus 2 plus, now we'll be, this will cancel this, so we'll have bx multiplied by x minus 1 plus c x minus 1. And this is our equation 1. So again, let's look at it. What would be good to get rid of some terms? So here and here, if we let x equal 1, this will be 0 and this will be 0. So we will have 8 plus 2 minus 1 equals 3a. 1 plus 2. And working out that, we will get a is equal to 3. Now, again, let's look at our equations. If we let a be x equals 0, this part here will become 0, and we'll get this tidied up. So let's let x equals 0, so we'll get rid of all those terms. This will be 8 equals 2a. This is going to be 0, so then plus c minus 1. And we know a is 3, so c will become minus 2 by letting a equal 3 here. Now we've got our we've got our A, we've got our C, we just need to get our B. So this time we're going to let x be minus 1. So if we let x be minus 1, we will get and we've got our A's and we've got our B's. So let x be equal to minus 1. We will get here 5 is equal to 9 plus 2b plus 4 by doing all the different substitutions in here. And then b will become minus 4. Not made that clear. So then our partial equation is going to be this. Rewrite that. I'm not going to have much space. So A was, where's A? A is 3. And B is minus 4. And C was minus 2 over x squared plus 2. And we can rewrite that as 3 over x minus 1 minus 4x plus 2 over x squared plus 2, because it's just a bit neater and tidier. Now, we can use this method with improper fractions as well. So all the examples we've done so far, we've had proper fractions. Now we can extend it to improper fractions. So let's do an example. So we've got x squared plus 5x minus 11 over x squared plus 2x minus 3. Now the first thing we're going to do is what we've been doing previously with improper fractions and turn it into proper fraction, like a mixed fraction. So we'll have our 2x squared plus 5x minus 11 divided by 2x squared plus 2x minus 3. So the first thing to look at is our 2x squared. How many times does it go into x squared? So it goes in twice. So the first one we're going to have here is 2. So 2 times this is going to be 2x squared plus 4x minus 6, and we'll substitute all that and we will get x. 5 minus 4 is x, minus 11 minus 6, so that's plus 6, becomes minus 5. Now we can't go any further, so our improper fraction has become 2 plus our remainder minus 3. Now, we're going to factorize this. So we're going to deal with just this part now. And we will factorize this quadratic. So we'll get, that becomes x plus 3, x minus 1. Now we have a fraction that we can put into partial fractions. And it's like our first example. So we'll have a over this linear function here plus b over x minus 1. We're going to multiply through by x plus 3, x minus 1. So we'll get x minus 5 is equal to a x minus 1 plus b x plus 3, and now we're going to let x equal 1 to get rid of that, so that's going to become 1 minus 5 is going to be minus 4 equals to 4b, so b is going to be minus 1, and then we're going to let x equal minus 3, so we'll get minus 8 equals, that'll be 0, it will be minus 4a, a is going to be 2, and now we have all our bits. So this here is now going to be 2 over x plus 3 plus, no, minus, sorry, minus 1 over x minus 1, and we can now put everything together to give us our partial fractions for our improper fraction. Let's just write this out. So we've still got our, don't forget your 2 that we got here, and that's going to be 2 plus 2 over x plus 3 minus 1 over x minus 1. And that's how you would do the improper fractions. Now, we can use this method to be applied to other types of sequence problems. So we're going to be looking at a geometric series in this. So let's say, given that the algebraic, sorry, this writing is terrible, algebraic fraction 1 over x plus 1 can be written in partial fractions as 1 over x minus 1 over x plus 1. Find the sum of the first n terms of the series 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5 plus 2. Hence, find the sum to infinity. So let's look at this series. So we've got 1 times 2 plus 2 times 3 here plus 1 over 3 times 4. And this continues until we'll get to, now look here, we've got n minus 1 times n plus n plus 1. Now this is like what we have up here. The terms in our series is the same as this algebraic fraction. We've got our x, then multiplied by x plus 1. So we can, instead of writing each term, we can use the partial fractions that we've been given. So this one is going to become 1 over 1 minus 1 over 2. And then we'll get plus 1 over 2, 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4, plus so on and so forth until we get to 1 over n minus 1 plus, minus 1 over n plus 1 over n minus 1 over n plus 1. Now we've got these minuses, so this and this will cancel, this and this cancel, this will cancel with the 4, and these are all going to cancel out until we get to this. So we're just going to end up with 1 minus 1 over n plus 1. Now as n tends to infinity, the sum of Sn is going to tend towards, is going to become, well, this part here, 1 over n plus 1, will tend towards 0. Because this gets really big, this will become really small. So the sum will go to 1 at infinity. Now this function here, this series that we've worked out here, is actually called a telescoping series because of the partial sums only have a fixed number of terms after the cancellation. So no matter how big n is, we cancel out and we're just left with these two terms. And this happens quite often. There's quite a few different functions, series that work like this. And by using the partial functions, we can explore these series and save ourselves a lot of work. So I hope all that helps.